So welcome to lecture 23. So let's continue on from last time. So last time we saw this notion of a graphical decomposition, and I can't remember if I wrote down the main theorem, but let's just write it down again just to remind ourselves what we have. So given a boundary decomposing projector P plus, a boundary condition, so we have that a boundary condition is elliptically regular if and only if B is L2 graphically decomposable. With respect to P plus. So that means that we have, so i.e. we have V plus minus plus W plus minus equal to P plus minus of L2 on the boundary, W plus minus star in H half and finite dimensional. And we have a bounded map that maps us from V minus to V plus, which descends to H half, to a bounded map, H half bounded map, so that the boundary condition B can now be written as the graph of G restricted to H half plus the W plus. Okay, so that was the decomposition. I just thought I'd write it compactly, just so we remember what it is. So if this is the case, so if one of these equivalent conditions hold, that either the boundary condition is elliptically regular or it's L2 graphically decomposable, so in either case, in this case, the adjoint boundary condition, we can also describe that. So remember, the adjoint boundary condition is related to the annihilator in the hat space, right? So the adjoint boundary condition, so it looks something like star of the adjoint boundary condition. This is actually equal to, as we recall, this is the annihilator now of the, now this is a pairing actually between the hat space of D and the check space of D. So we didn't prove this, but we don't really need to. I mean, the same argument as in the case of the spectral projectors goes through in this situation, right? So this is a perfect pairing, and this is in fact now equal to the adjoint. Oh, I forgot to say that. So it's not. We also need a condition on the G star. So maybe I'll just move all of this down. So this descends to a bounded map, G adjoint, which takes us from V plus star to V minus star, also descends to H half bounded map. And we have this decomposition. So now the point is that this boundary condition can be written in terms of the adjoint. And I had it wrong the last time, so it's a good thing that I'm writing this now. So this is V plus star intersect H half of the boundary And of course there's an error term, right? So what's the error term? It's exactly going to be W minus star. Okay, so here we have W plus star, and now we have a map that goes in the other direction from V plus star to V minus star, and then the error term there we'll pick up is the W minus star. Okay, good. So let's give some examples. So let's just start with some examples first. So we will prove this, but I want to really look at consequences of this to really motivate why we need a seemingly obtuse characterization of a very nice qualitative property, right? And the point is this is extremely useful in calculating. So okay, so the first example, so let A be an adapted boundary operator for D, and A is, now I want this to be the half of min lambda minus lambda 1 and lambda 1, where lambda j is in the real part of the spectrum of A, right? So we've seen this before, so this is what we use to define the APS boundary condition. So then by design, this is invertible bisectorial. And we've already seen that P plus, setting P plus to chi of A, is a boundary decomposing projector. Good. Now let V plus minus equal to chi plus A, or plus minus A of L2 on the boundary. We'll make the W plus minus equal 0. And the map G that takes us from V minus to V plus, we set defined by setting it identically to 0. Okay, so then what is the boundary condition we get? So the graph of G restricted to H half plus W plus is simply equal to what? It's equal to V plus 0V, such that V is in V minus intersect H half on the boundary. And that's just simply going to be V minus intersect H half on the boundary. Oh, I should maybe put chi plus chi minus L2 intersect H half on the boundary. And what is this equal to? This is precisely equal to chi minus A of H half. And that is our APS boundary condition with respect to the adapted boundary operator A. Okay, so we can see how this comes about. So okay, so what happens if we choose a different spectral cut? So if we choose a different spectral cut, what will happen is we pick up this error term W plus, okay, because we still want to describe the APS boundary condition in terms of some B. So here we've chosen the spectral cut to coincide with so I should say well, maybe in 2, if we chose AR for R not equal to A, then the spaces W plus minus need to be chosen appropriately to describe BAPS-A as a graph. Well, graphically. Okay, so if we change the spectral cuts, of course we need to account for the error that we pick up by cutting elsewhere. Okay, so let's have a look at another example, which I think is somewhat illuminating. So let's take M to be compact, and in this situation we can let P plus be a Calderon projector, right? A Calderon projector. Then with the choice of V plus minus equal to P plus minus of L2 over the boundary, W plus minus again is 0 and G is 0 identically, we obtain that the induced boundary condition is going to be the graph of G intersect H half plus W plus. And what's that? That's exactly the complementary subspace via this Calderon projector to the Cauchy, the Hardy space of solutions. So okay, so this is now H half, right? So from this, actually, we obtain, because we can write it down graphically in this way, we automatically obtain from having proved this theorem that the complementary subspace to the Hardy space of solutions is actually an elliptic boundary condition, or elliptically regular boundary condition. So from theorem, B is elliptically regular. So the main point here is that we also get that the point, i.e. by construction B is in H half, but we also obtain that B dagger, the adjoint boundary condition, is also in H half, right? So that's really what we get. That's a non-trivial statement here. So the other thing to note that the kernel of the operator dB now is equal to the kernel of the minimal extension. Okay, because since the Cauchy space is the restriction to the boundary of the U in the kernel. Okay, and the 1 minus C kills, and 1 minus P of C is 0. Okay, so so the only thing is it's whatever's in the intersection, right? And whatever's in the intersection now is just going to be the kernel of d min intersect dom d min, right? Because in the check space, the 0 element corresponds to the minimal extension. So, okay. So let's have a look at something slightly more advanced. So in 2, let us modify the construction by choosing some W plus in the solution the Hardy space of solutions intersect H half finite dimensional. Okay. So in this case, we have 1 minus PC of B plus, now we have some finite dimensional error term. We're allowed to do that in prescribing a boundary condition in this way, right? So, okay, so maybe I need to also just ensuring so let me see. Yes, ensuring W plus star is also in H half. Anyway, so if we were to do that, then we set a boundary condition in this way, define it in this way, and so what happens? So now we have that the kernel of dB is equal to the kernel of dW plus. So this is U restricted to M, U in the kernel of D max, such that U restricted to partial M is in W plus. So what's the advantage? What are we gaining out of this, right? So what we're gaining out of this is that, I mean, we talked very early on in this topic about boundary value problems and separating the problems part from the boundary values part. So here, if we're landing in W plus, I mean, we're in the kernel, so these are solutions. So the Calderon projectors are very useful in that they allow us to understand the problem aspect, right? At least on a compact manifold. So so let me remark on this, right? So remark. So early on, we discussed separating the boundary value part from the problem aspect, right? However, from 3, it is tempting, at least historically, well, I should say the other way around, right? From 3, at least historically, it is tempting to see these aspects together. So the advantage of having an elliptic boundary condition describing this is that we know that, so I should have said here, okay, I'll say here, the advantage of some desired solutions in the Hardy space C of regularity H half arising as the kernel of dB for B elliptically regular is that dB is Fredholm. Okay, so we we have a finite dimensional kernel, finite dimensional co-kernel, and you know, it's much nicer to work with such an extension that has very nice regularity properties, and we can try and do all sorts of things with it, right? So, in 3, what we have is a boundary condition B with prescribed solution space W plus yielding dB, i.e., so what do we have? We have precisely du equals 0 with u restricted to the boundary being in this W plus, but with u in dom dB, where dB is elliptically regular. So the solutions we're interested in is actually a much smaller set, right? I mean, of course, an elliptic boundary condition on a compact manifold is always going to have a finite dimensional kernel. But we might not have control on that kernel. So here, using this theorem, what we can do is we can start off with some solution set that we like. This is living in this the Hardy space of solutions. And then we have the a complementary part, which arises from the existence of a Calderon projector. Actually, it doesn't matter which complementary part we choose. And then when we just tack it on together in this way, the theorem now tells us that we have an elliptic boundary condition. And of course, a direct calculation then tells us that the kernel of the dB has to be the kernel of dW plus. So if we just started off with dW plus, which is a finite dimensional subspace, and we considered that as an operator, we will not get a Fredholm problem, right? So the advantage here is that we get a Fredholm problem. Maybe I should actually explicitly say that. If we considered the operator dW plus, this will not be Fredholm. Okay, so it's sort of weird that if we're interested in solvability, the first thing we should do is to look at the part that doesn't solve and add that together in a way that the boundary condition we end up with eventually has nicer properties, and it also has the solutions that we desire. Okay. Let me just continue the remark a little bit more. We see, however, from a global analysis point of view, as in 1, the spectral projectors of associated adapted boundary operators offer a different geometry of the check space, better suited to another class of problems. So the real power of this theorem is that it allows us to decompose the check space, decompose an elliptically regular boundary condition from any imposed geometry on H check of D, i.e. For any boundary decomposing projector. Okay, so it can be useful depending on, you know, which problem you're interested in, and I can't stress this enough. Sorry. So the real point is that when you have elliptic boundary condition, you can think of sort of the boundary decomposing projector as almost something like a coordinate system. And if you think about it in that way, what it's really saying is it allows us to decompose this elliptic boundary condition or elliptically regular boundary condition now in terms of this, if you will, a coordinate system on the check space that is suited to whatever problem that you want, right? So that's really the take-home message from all of this. Okay, the main application, so one of the main applications of all of this is the relative index theorem. It's due to Gromov and Lawson, Gromov and Lawson originally, and it was done with very, very different techniques, and it was a seminal paper in the field. And what I want to go through before we get onto the proof of this elliptic decomposition theorem, which will take a few lectures, it's quite cumbersome, is to initially show how to use this theorem to give a proof of the relative index theorem, right? So let's start this new section, the relative index theorem. So the relative index theorem is really an index theorem that's useful in a non-compact setting. Okay, so it's not really interesting in its own right in the compact setting. So we need to be able to talk about index problems and Fredholmness for operators that live on non-compact manifolds. So we need some sort of control. We need some sort of control of what happens at infinity, right? So let's start with the definition. So okay, maybe I should write that here. So the relative index theorem has its non-trivial applications in the non-compact setting. So to talk about Fredholmness, we need some control of D at infinity. Some additional control. Of course, we always have the background assumption that these operators are complete, but we need something beyond that, right? So that's what the next definition captures. So definition. So let's take elliptic differential operator acting between E and F. Elliptic. So we say that this is coercive at infinity if there exists a compact set K and a constant such that the following hold, such that U in the L2 norm on the manifold is going to be bounded via this constant against du L2 mf for what class of U? So for all U in C infinity C M E with the support of U contained in M minus the compact set K. Okay. Okay. All right. So that is interesting. So what it's really saying is that we can have some topology maybe of a manifold. We have some topology, and then as we go out to infinity, so this is going out to infinity maybe, and I'll say this. So this is the compact set K, and things can happen here, right? So things can happen inside this region. Things can happen, non-trivial things can happen, but out here, things are nicely controlled, right? So that's a pictorial depiction of what this is capturing. Okay, so let's start with some examples. So the first is when M is compact, set K equal to M so that every elliptic D is coercive at infinity. Okay, so this generalizes the situation for the compact case, and I mean that's very easy to see. So a second example. So I think in the tutorials, there's also already been discussions about Weizenbach formulas, particularly in the Dirac type setting. But let's talk about a particular Weizenbach formula. So since we now have the advantage of having at least seen spin manifolds in a pedestrian way, let's assume that M is spin. Yes. 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 So what? Yes. I mean, the point is that of course it's no condition at all, but the point is that when M is compact, it doesn't matter, right? I mean, then there is no condition. That's what it's really saying. Right? Because when M is compact, K is the set. And then we can allow for all U and it can do whatever it likes. Okay, so suppose M is spin, or Mg is spin Riemannian. And D is the spin Dirac operator. Of course, after choosing a spin structure, right? So the Weizenbach formula, then the Weizenbach formula says what? it says that d dagger d of u is equal to connection dagger connection of u plus 1/4 the scalar curvature of G acting on U. So where SC of G is the scalar curvature of G. So let's now suppose, for our purposes, so suppose that SC of G is greater than or equal to some kappa. I can never draw a kappa. Outside some compact set K in M compact. Okay, so then how do we get the coercivity estimate? So let U now be in C infinity C ME with U, the support of U in M subtract K. Then I'll begin with the square of this object. So we now get that this is D dagger D UU, right? So I just expand the inner product in terms of, expand the norm in terms of the inner product. And because, because, okay, I have to be a bit careful here. Okay, I should also remove the boundary. Okay, so outside K compact. So the boundary is always compact, right? So suppose outside of K compact, outside of I'll put maybe K prime compact. Let K. So let's let capital K now equal K union some boundary of M epsilon. Maybe I'll call that a ball centered at the boundary of M epsilon closure, right? So this is now guaranteed to also be a compact set. So I've just increased my compact set a little bit, and then I'm guaranteed that this section U now stays away from the boundary because I'm asking for the support to be less than the boundary. And then, of course, this works, right? I don't get a boundary contribution when I pull across the adjoint. And then the Weizenbach formula gives me this quantity plus now 1/4 the scalar curvature of GUU. Well, that's good because I can now again pull the formal adjoint across without worrying about any boundary contributions for the reason I've said it. So now I have that this is, just the norm of U squared plus 1/4. So now the scalar curvature of G was assumed to be, I should say this is a positive number, right? This is a positive number, so then the scalar curvature of G is positive in the part that I'm looking at, and therefore it pops out. So this becomes now kappa, and now this is U squared. Okay, so then, and this is not an equality, of course this is an inequality, and then this is of course now going to simply be bounded by the kappa, which I cannot draw, on 4 norm U squared. Okay, so this is somehow the intuition of this condition of being coercive at infinity. Basically, actually the history of the relative index theorem is really in the study of scalar curvature. So what you really care about is whether you can find metrics which have non-negative scalar curvature and extract out the problem in terms of a problem on operators, right? And this now gives us obstructions to the existence of such metrics because we have the Weizenbach formula coupled with what we'll see later as a relative index theorem that allows us to study these questions. So that's really the history of this sort of idea, and this coercivity at infinity is somehow also coming from this sort of Weizenbach, these calculations that you can do once you have a Weizenbach formula floating around. Okay, so now that I've given a couple of examples, let's try and characterize this condition, right? So D is coercive at infinity if and only if there does not exist a sequence UN in compactly supported smooth sections on the interior, supported on the interior, satisfying the following. 1, UN on ME is norm 1. 2, the limit of DUN of L2ME is 0. And the third point is that for all K tilde in M compact, there exists some large number nk tilde with such that whenever n exceeds this nk tilde, the support of the UN intersect the k tilde is empty. Okay. So before I talk about the theorem, actually, or the proof of the lemma, let me just say that it somehow sounds a bit strange when you characterize the condition by saying that there does not exist a sequence. In fact, I think the nicest way to try and understand this is to take the contrapositive, right? So you can take the contrapositive equivalent statement and instead think about what it means for D to be not coercive. So equivalently, we can say D is not coercive at infinity if there exists a sequence satisfying these properties. Okay? Okay, so we prove the proof. So we prove the statement by the equivalent contrapositive. In both directions, right? So let K1, K2 be an exhaustion of M. With Kj compact. Okay, so such an exhaustion always exists. We saw that very early on. Okay, so let's consider this. So if D is not coercive at infinity, so what does that mean? So if it is coercive, it means that we have a compact set for which we have this bound. But if it's not coercive, it means that so we can find compact sets which violate this bound, right? So if it's not coercive at infinity, for each natural number j, there exists some Vj which is compactly supported, smooth, Me, such that the support of the Vj intersect the Kj is empty, and Vj exceeds J dVj. Okay? So now let Uj define this to just be the normalization of this Vj, right? So let's just normalize it so that the norm of Uj is 1. So normalizing this expression, so what we get is then d of Uj is less than or equal to 1 on j, and this goes to 0 as j goes to infinity, right? Okay. So that proves it one way. So if it's not coercive at infinity, I've just given you a sequence for which this is satisfied. So what happens in the other direction? So suppose, remember again, we're proving the contrapositive. So now suppose that there is such a sequence, right? So suppose we have such a sequence. So for the converse, suppose such a sequence exists, then it is easy to see that the definition is violated. Okay? So that proves the theorem or the lemma. Okay. So now let's really understand this the connection between this coercivity at infinity and a boundary condition being elliptically regular. So here actually we don't really need the graphical decomposition. What's really required here is the regularity, right? So in fact, the B here can be replaced with semi-elliptically regular, which just means that it's a boundary condition sitting in H1/2, right? So proposition, in fact, maybe I'll state it in this way. If B is semi-elliptically regular, i.e. B is a boundary condition and B is sitting in H1/2, right? So we make no statements about what happens on for the adjoint boundary condition. So we've already discussed this. We get from semi-regularity to regularity by imposing this on both on both these things. Okay. Right. So now, okay. Then D is coercive at infinity if and only if dB has finite dim kernel and closed range. Proof. Okay. Okay. So let's suppose that, so let D be coercive at infinity. Okay? So what do we want? Okay, so and let un be a bounded sequence in DOM-DB, so in the graph norm, such that D of un converges to V. Okay. So now let K be the subset, compact subset from the definition, and so let chi be a cutoff function. So this is a function that's going to take values in 0, 1, with chi equals to 1 on K, and with K prime being equal to, well, let's set this equal to the support of chi. Okay, so I mean it's a smooth function, so and we take it to be compactly supported. So by construction, we'll have that K prime is also compact. So what does it mean for B to be elliptically regular, right? So B elliptically so B in H half E. So this implies that the domain of DB. So this is actually an if and only if statement, right? So this is if and only if. So this is just the regularity statement that we had some time ago. So we have B sitting in H half, and that's if and only if that the domain of DB is sitting in H1 lock of ME. So therefore, we have what? We have that the so then we have that the chi of u with respect, so for any connection, right? Because remember, for the lock space it doesn't matter. So for any connection, for any fixing a connection, I should say, fixing a connection nabla on E, we have what? We have that this K prime plus U L2K prime. So this is now controlled. So this is now equivalent, in fact, to dB of chi of U, L2K prime. Well, maybe we don't need to write the K primes here because they're local operators anyway, right? So this is on all of n. Because but then I have to include the chi here. But I'll do that. Okay, it's fine. L2 of ME plus chi U L2 ME. Okay. For U, for all U in DOM-DB. Well, actually, it's really this direction, right? So let's write the estimate in this way. Okay. All right. So now the point is, dB of chi U is what? This is precisely chi of dB of U plus the symbol acting now on dx of U. Good. And so what we have is that the chi of um minus un is going to, in the h1 k, well, it doesn't even need to be k, m e norm. Wow, okay, that's a problem because, of course, yeah, it should be k prime e. Because of course then I'd have to write h1 lock, but let's just concentrate our attention just on the compact set k. So this is the exact norm that we wrote here, right? That's this norm. So this norm is now bounded by chi of dB, chi of dB of minus un plus, now I have this d chi x minus un plus now the norm here that we had of chi of minus un. And of course, this symbol is also compactly supported, right? It's a smooth object that's compactly supported because of the properties on chi. So that means that this whole thing is going to be bounded by minus un in the dB norm. But by design, this goes to 0. And the right-hand side goes to 0 as mn go to infinity, right? Because it's Cauchy. We have this, that d of u, m converges to some v. Okay. Okay. So how does this help us? Okay. So now. So this allows us to control just the term sitting inside this compact region, right? So the regularity comes in to control what happens in the compact region. So now, this following estimate is very instructive. So minus un now so this is in the L2 norm, right? So this is in the L2 norm, sorry, not the boundary, me. So this is now going to be bounded by chi of minus un in L2 me, plus now I have a 1 minus chi, right? So nothing fancy here. And so what's the point now? The point is that, okay, so the first term we understand, right? So the first term we understand. The second term, so let me just write this minus un L2 me plus, but now the second term, so this term is supported away from the compact set K. So then we can use the fact that the operator is coercive at infinity. So this is now going to be d of 1 minus chi minus u, it should be n. Okay, so maybe big brackets here. Good. Okay, so we have that. Right. And then so from this, what do we get? So then from this we get, this is a un, yes? So now we get again the chi of minus un, and now we have, so this is again in L2 me, and now we have this term which is d of this thing is just going to be dx again, so minus un. And now we have this term which is 1 minus chi d minus un. Okay, but now again, as before, this term is harmless, right? So this term actually so I should say, so what happened here? So so we absorbed this term into, yes, so it's in the graph norm that we have this. So now this gets absorbed into the graph norm, right? So okay, let me see. Let me just see for a moment. Yes, so this can now be absorbed into the graph norm. So we have minus un plus, now we have minus un in d. But this now heads to so this whole expression now tends to 0, right? So this goes to 0 as mn tends to infinity. So the point is, so what's really the idea of this expression? The idea of this, not this expression, this estimate. So the idea really of this estimate is that we need to be able to control minus un in terms of, and show that this is in fact a Cauchy sequence when we just start with the fact that we have a bounded sequence in DOM-DB with DUN converging to V. Okay, so I should have said, okay, I wasn't quite truthful in this estimate. I will fix that in the lecture notes, because of course this is not converging in the graph norm. This is just DUN converging to V, right? So we need to, so how do we really get control of the object as we need it? The real point is that this is a bounded sequence in DOM-DB. So it has a so the ellipticity allows us to obtain a convergent subsequence in the so this is all up to a subsequence that this is true. And it allows us to obtain a convergent subsequence through the Relish embedding theorem, right? That's really the point. I will fix that in the lecture notes. Anyway, up to a subsequence, this is true. So that means that there exists some u in L2 ME such that m converges to u. And since DB is closed, we have that U is in DOM DB and V is equal to DB of U. Okay. All right. So the proof in the other direction. So sorry about that. I do need to fix it. That's an oversight on my part. And really the point here is that yeah, we cannot just control it using the DB norm here because we don't actually know convergence in U. Of course, if we knew that, then it'll be trivial, right? The point here is that we have a bounded sequence and D of UN converges. So we have to really be able to control things in terms of just the D of B of U. And the lower order part is really accounted for by a Relish argument in here, and then the remaining term is controlled by the fact that we have D of UM minus D of UN converging. So I should really write D of UM minus UN here. Right, and everything has to get absorbed into this term here. So that's a slight oversight on my part, and that's still okay because see D of X is supported now in the set K prime. So actually we have to really run the Relish argument here in K prime, and we really can, we can obtain this convergence without the chi here, right? We choose a different cutoff here so that we see the full set K prime, and then we can absorb this derivative term also. We can absorb it into the lower order term, right? So I will fix that in the lecture notes. Okay. So let's prove this by the contrapositive, the opposite direction. So proof by contraposition. Okay. So suppose D is not coercive. Then by the lemma, we have UN compactly supported in the interior, which on taking larger and larger compact subsets Kj have support U nj intersect Kj is empty. So, from a weak convergence point of view, this converges to 0 for all f in C infinity C. Okay? Since the norm of un now is equal to 1, we have no convergent subsequence in DOM DB, and in particular L2. But we also know from the second property that dB of u at u goes to 0, right? Well, I should write but. So, since, oh, well, I've said since before. But the norm of dB of u and j goes to 0, and if dB had a finite dimensional kernel with closed range, then every bounded sequence un or vn in this form with dB vn converging to some w has a convergent subsequence. So to avoid contradiction, we have to assume that it does not have closed range and finite dimensional kernel, right? So that proves that proves the statement. So the nice thing about this proposition is that it allows us to try and understand the condition of an operator being coercive at infinity from imposing a boundary value or imposing boundary conditions, right? I mean, we have operators which have elliptically regular boundary conditions, and that can be used to detect whether the operator is coercive at infinity or not. Okay, and the corollary, this is the important corollary, if D and its formal adjoint are coercive at infinity, and B is elliptically regular, then dB is Fredholm, right? So despite this manifold being non-compact, it's Fredholm. And so the index of dB, which is the dimension of the kernel of dB minus the dimension of the kernel of dB annihilated dagger. So this is now an integer. Okay, so we get an actual number, which is good. All right. Okay, so now let's so what do we want to really work up to? We want to work up to being able to deform boundary conditions in some nice continuous manner. Okay, so deformations of boundary conditions. Yeah, sure. I mean, so the question was, how we define the index in this way? Well, the index is the dimensional of the kernel of the operator minus the dimension of the co-kernel of the operator. So the co-kernel is is L2 mod out, the dimension of L2 mod out the range of the operator, which we know is closed. So if it's in the conditions that we've stated so far, so then what happens is, of course, the co-kernel can be the co-kernel is isomorphic now to the kernel of the adjoint of the operator. Okay, that's true. I mean, beyond boundary value problems or whatever, we've seen that already. So if let me get to that. So the point is so now we have the kernel. So what is okay, maybe I should make a remark just to avoid the confusion. Remark, note that dB dagger dagger is equal to dB star. Okay? So the point is that the D dagger B dagger is the D dagger operator with the adjoint boundary condition. Right? In fact, that's the definition of the B dagger. So that's exactly what this is saying here. So this is saying that this is equal to the dimension of the kernel of dB minus the dimension of the kernel of dB star. I mean, that's true in general, but because we have boundary value problems, we can further identify it in this way, right? So that's all I'm saying. Right, okay. Okay, so now let's talk about deformations of boundary conditions, right? So definition. So a family of boundary conditions so BS in H check of D for S in 0 to 1 is a continuous deformation from, of course, the B0 to the B1 if there exists isomorphisms phi s taking us from B0 to BS, phi 0 equal to the identity with S mapping to phi s being a bounded map. So this is a bounded map from so these are bounded maps in particular in the H-check norm, and we want the map in the parameter S to be continuous. Okay, so each map takes me from B0 to BS boundedly in the H-check norm, right? Of course, this makes sense because the BS's, I mean, we're talking about boundary conditions here, not generalized boundary conditions. So the BS's are all closed subspaces of H-check. So the norm that they absorb is precisely the H-check norm. And now I want this to be a bounded map, so I wanted to take B0 to BS boundedly. So of course that's going to happen in the H-check norm. But in addition, I want in the parameter S, I want this to be a continuous map. Okay, so i.e., so maybe I'll write a quick remark. i.e., the phi dot is a continuous map from 0 to 1, landing us in the Banach space, which is B naught H check D. So I didn't want to write it in that way because it's a bit cumbersome, but anyway. All right, so an exercise. Suppose that the BS are elliptically regular, then S maps to phi S. So this, well, I don't need phi S because it's true, but I should just say phi S is in B naught H half of D M E, right? So that's the statement. So this should really come out of the wash. Okay. So now I'm going to somehow fly a bit off the rails because I haven't. So let's see how we can prove this, right? So this next proposition. Suppose that phi of S, so phi dot say is a continuous deformation. Oh, that's probably ugly. S maps to phi S is a continuous deformation of boundary conditions. Then there exists capital phi S that takes me from boundedly B from dom D B naught to now where? So this takes me from dB naught to let me think. I need to be in dom D max such, well, okay, I should say S mapping to this exists, S mapping to this continuously such that capital phi of S dom dB naught is equal to dom dBs. Okay, so the proof of this. So how would we prove this? So maybe I'll actually call it a proof sketch. Yes. Yes. So I'll give a proof sketch. So the proof sketch is as follows. So so what do we have now? So we have, so recall that dom d max mod out dom d min is of course isomorphic to the check space, right? We already know this. Therefore, so since dom dB is a closed subspace of dom d max, right? That's because B is a boundary condition, right? So we have that dom dB mod out, well, dom, I should say dBs, mod out dom d min, of course, is a closed subspace of dom d max now, mod out dom d min. And therefore dom dBs mod out dom d min is isomorphic to BS, but the point is that this isomorphism with constant independent of BS, right? So this constant really just comes from the fact that BS embeds into the check space. And that's just an inclusion map, right? Okay, so then we can write DOM, well, this is a Banach space isomorphism. So there are constants involved in the norms. Okay, so now the point is that DOM DBS is of course going to be isomorphic to DOM DBS mod out DOM dmin plus DOM dmin. And so what? So this is now isomorphic to BS plus DOM dmin. And what is the BS? So the BS is phi of S B naught plus DOM dmin. Good. Sorry, little phi of S, right? Okay. And this is an isomorphism, right? So this is B naught plus DOM dmin. Of course, this is where we use the phi S, right? So this is where okay, let me just make that remark, because maybe this is something good to work out in an exercise to actually really calculate what this isomorphism is. DOM dmin. So I should, okay, so this is DOM dmin plus DOM dmin, and of course this is now DOM dB naught plus DOM dmin. So it's in the 1, 2, 3, 4. In the fourth isomorphism, phi S maps to phi S is continuous and determines the phi S DOM dB naught to DOM dBs continuously. The conclusion follows. Okay, so I mean, this is no surprise. You have a continuous deformation of boundary conditions. The boundary conditions, of course, induce the operators, right? Again, the picture really here is that, you know, the check space is really DOM D max mod out DOM D min. So if you have subspaces in there and there's some continuity conditions in the way that we deform those subspaces, then we should also expect the induced operators to also deform in a continuous manner. And that's precisely what we're seeing here. So next time we will use this to think about how to couple this with elliptic boundary conditions and start thinking about deforming elliptic boundary conditions, right? So maybe I'll leave it here for the moment, because to be honest, I didn't even prepare this proof. I just sort of whacked it out of my head because I've had a bit of a busy week. I haven't had too much time to prepare, but I think this holds water. Okay, so thank you, and see you next time. Yes. Any questions?